righty, let's see what we got here. All right. How do I get rid of this mode here? Let's see. All right. All righty, let's see. I don't know how to get rid of this. Well, hear me okay out there?
Yeah, we can hear you.
Thank you. Appreciate it. All right. Let's see if I can figure out how to bring up. Okay. All righty. Welcome back to the show here. Let me go ahead and log into the homework real quick. Let's see. So I believe last time we had finished the section 3.1 with the mean, median, and mode. And now we shall move forward into measures of variation. Sounds exciting, doesn't it? I can tell. Measures of variation in shape. So without further ado, I'll go ahead and begin here. So now we're looking at, with measures of variation of shape, we're looking at measures of variation specifically, kind of how far scattered apart are the data values. You know, they more concentrated toward the mean in the center, median maybe, or are they more spread out? So that's what we're looking at in this section. Now the first and the most basic measures of variation is the range. And the range is very easy. It's just the maximum data entry minus the minimum data entry. That's just a fancy way of saying your largest number minus your smallest number. Now, if your data is sorted from lowest to highest, then it's really easy. So obviously, if you have data that's in Excel, you can just sort it, especially if there's a lot of numbers. That's what I would do. Sort it, because then you know that I started to say the one on the right. If they're written horizontally, it's on the right. If you sort lowest to highest, it'd be the one on the bottom of an Excel column. But if they're not sorted, you got to look through there and find, which one's the largest, which one's the smallest. So in this set of data, the 24 would be the largest number and 2 would be the smallest number. So 24 minus 2 would be 22. So that's pretty exciting, isn't it? Range. Now I'm going to kind of go through a little bit how the mechanics of how this is sort of calculated, but you're not going to really have to sort of really do it this way, so I wouldn't worry too much about this. But I just want to kind of show you a little bit here. But this will be, technology based. Whether it's Excel or whether it's a TI calculator. Now I'm going to mention what's called a deviation of a data value. That means whether it's sample or population, it's calculated the same way. You take whatever your data value is and you subtract whichever mean it is, and that gives you what's called a deviation value. Now let's look at this. I'm just labeling this as a sample. It wouldn't matter that much, but it's sample right now. It'll be population later, which actually is going to make a difference in the calculation, surprisingly. Not for the mean, but for the next thing we calculate, it makes a difference whether it's sample or population. All right, the mean's simple enough. You just add them up and divide by how many you have. And we get 9.2. Now, if we're trying to figure out how scattered the data is, if you go back to these deviations, suppose that if we took the deviations and let's say, well, what if we just average the deviations, come up with some number that represents an average of the deviations? Well, the problem with that is did I do it for this? Well, we can do it. We don't need to, though. It's not that important, but you could double check this. But I guarantee you any data set you make up, this will be true, is that the sum, so that's your deviation right there in the parentheses. This means the sum of all the deviations in a data set is always going to equal 0. And we could prove that using the formula if we wanted to, but we don't really need to. But yeah, you can't prove it equals 0 mathematically. But that's no good, because if it adds up to 0, you divide by n how many numbers you have, that means you're going to get 0 every time. That doesn't tell you anything, because there's only one way a data set can have no deviation. That's if every number is exactly the same. So that would be a pointless way to do it. So this idea came about. Well, what if, so if the deviation, if it's like -2 or +2, we don't really care that much whether it's negative or positive. We're more concerned, the distance it is away from the mean. That's what we're more concerned about. So to eliminate the idea of having to deal with the negatives is that you square each deviation. That means you're either going to get 0 or positive for every deviation. That would solve the problem of them adding up to 0. Now they won't add up to 0, well, unless every number was the same. That's the only exception. But now, if we square each deviation and we add those up and we divide by n minus 1, and there's a whole thing on the n minus 1. I think I got something put in the notes here later we'll look at. You don't have to worry that much about it conceptually, but just know it's there. We call this S squared. That's called the sample variance of a data set. Sample variance, where it's squaring up all the deviations, squaring and adding them up, and then dividing by n minus 1. So if you have like 5 numbers, you'll divide by 4. So here's kind of the shorthand formula using the summation notation. And this is just a term. This is called the sum of squares. What we're doing right there, that whole numerator is called the sum of squares. So like I say, you're not actually going to have to do this. I'm just showing this to you. That's why we're not going to spend a lot of time on this. But yeah, if you were doing this using the formula, I mean, you'd still be using a calculator, but we take each number, the mean, the same data set that's right up here, 9.2 is the mean. So I'm taking each number, 12 minus 9.2 squared, 13 minus 9.2 squared, so forth, so on, adding those up. I didn't calculate those individually because I just put it in a string there in the calculator where I just strung them all together, because I don't care specifically about each individual term in the sense that I need to add the terms to get to the total, you know, so each one doesn't matter, but the total of them matters. So I did that, I got 44.8. So to calculate the sample variance, we take the S squared's 44.8 divided by 5 minus 1, 4, and you get 11.2. Or this one happened to come out kind of nice, but obviously if it's some bunch of decimal places, you'll just round to the appropriate decimal places that my math lab asks you. But on an exam, it'll be easy because you'll be visually looking at the answer choices, so you'll know how it's rounded. But obviously, we got to watch the My Math Lab, right? We got to make sure we do what it tells us. Let's see. So that's just showing the sample variance formula. Now, here's another definition. Sample standard deviation. Actually, standard deviation is more often used than variance, and they relate to each other by one quick calculation. The standard deviation, sample standard deviation, is the square root of the sample variance. Meaning if you have already calculated the variance, to get the standard deviation, you don't have to do anything other than just taking the square root of that number. That is it. In fact, anytime, I should have this mentioned coming up here somewhere. Yeah, we're going to have other formulas coming up in this class where we have a variance formula given. Whatever the variance, anytime you have a variance formula, the standard deviation will always be the square root of that formula. Every time. So that's by definition, that's what standard deviation means. It's the square root of the variance. And the reason why it's commonly used, we'll see more later, it relates better with the mean. And another reason is because when we go through and square those deviations, you know, we've kind of increased the values a lot more, you know, made them maybe out of touch a little bit. So square rooting it back down makes sense. Going back to what I was saying earlier, let me show you. Let me switch over to, we got a note page going here. Oh, get rid of that. Oh, John, you'd appreciate this. I was helping one of my calculus students earlier. I should have sent her to you. So we don't want any of that, don't worry, but we're going to have
you want her to learn.
I should have sent her to you for derivative tutoring.
No.
But anyway, we're going to have one later. It's going to be this. It's called NPQ. That's going to be the variance. Well, that automatically guarantees that the standard deviation will be the square root of NPQ. Automatically, even though we don't know what NPQ are yet, we will. But yeah, I'm just pointing out the idea of standard deviation always being the square root of variance. All right. And so here you just see, once we had this 11.2 calculated, we could get the standard deviation real easy by taking the square root. And that means it works, you know, both ways. And I want to show you the TI calculator. I'll show you what I mean here, because the TI calculator only gives you standard deviation, but to get variance, you have to actually square the number. So let's say, so it works both ways. Let's say if you know that S squared is, I don't know, 25. That's the variance. And you want to know the standard deviation. I'm kind of picking numbers here that I don't need to use a calculator for. It would be 5. But what if you were given the standard deviation and you wanted to know the variance? To get from standard deviation to variance, you square it. So it works, that's how it works both ways. You know, to go from variance to standard deviation, you square root. To go from standard deviation to variance, you square. Isn't that exciting? I knew it would be. All right, okay, since we're going to be using pretty much technology at this point, I think, is whether you're using Excel or Calc. This is people maybe, you know, I kind of always did this when sometimes I've had students just using a basic scientific calculator. And then that's where these formulas would have been necessary if it didn't have any kind of, you know, variance or standard deviation in there. But since you can use Excel, or if you are using the TI, I'll probably go back to this whenever we go back to face-to-face classes. But this is really not necessary, I think, at this point. You're not going to need to do this. It's just a different way to do that calculation. Like I say, this is helpful for if someone's just using a basic scientific calculator. But anyway, now I'll show you how to do this, and actually I'll wait, you know, I'll look at this one real quick, and then maybe I can do a new one in the homework. If it's not too many numbers, obviously with a bunch of numbers, we'll just do Excel and not worry about it, because that'll be easy too. But I just want to show people how to do this in a TI calculator. But I might just make up a new set of numbers here and do it in a minute. So you go stat edit. That's how you always build a list of numbers, is to go stat edit, and brings up your list menu. So you put all your values. So that's that same 5 I was working earlier. And then I always go quit. So I go second quit button to quit to get out of that. And I go back to stat. I go to calc, and then I choose that top one var stats. Hit enter. And as long as your information's in L1, that's the default column, everything will be fine. But we'll try this out again here in a minute. Now, actually, we're going to talk about that. There's actually 2 standard deviations here, but there's the S. That's the one we're studying right now, the S. So there it is, 3.3466, which I rounded up here earlier to 3.347. Right there. All right. So, but anyway, my point is the calculator does not show variance. So you would have to actually take that value. I didn't even use all the decimal places. I put a few in there though, put 5 in there. Hit the square key. So to go from standard deviation to variance, I squared it and got 11.999. Okay, so there's the 11.2 right there. So, okay. But there's a direct command in Excel that will do both of those, so you don't really have to worry about that. All right. Okay, here's where I did this formula business. This one might be a good one, actually. Put in the calculator real quick. I'm going to show you a different way to do this than what I've got down here. Yeah, we'll do it that way. But anyway, we can do. I'll show you that other one. It's not important. Okay, we don't need all this mess right here. I should have woke up the calculator earlier, but so you're not going to have to worry about using that formula. But I'll put this one in the calculator as soon as the calculator wakes up here. Forgot to wake it up before we started. Come here. Wake up. Okie doke. So I'm going to go stat, edit. Now I could clear that list, or since I know I'm going to be putting in more numbers than it's already there, I'm going to, I can just type over it. But to clear it, you go up here to the top and hit clear. And it's weird because nothing happens. But as soon as you move your arrow down, then it all goes away. It's weird how it works that way. Seems like as soon as you hit clear, it would just make sense for it to go away. All right, 3, 11, 15, 2. Let me memorize these a few at a time. 3, 11, 15, 9, 8, 6. So there they are. So I'm going to go second, quit. Then I'm going to go stat, calc, 1 var stats. So it's got L1 there as a default, nothing there. If you're using like an 83, it's just going to be blinking one var stats. You just hit enter. Don't have to do anything. So if you're using 83, just hit enter. Here you got to get down to the calculate before you can hit enter. And then there it is. It's the SX. So it's the 4.355 whatever. And let's see if that's what I have here. Come down here. 4355, that's just rounded. Now, of course, to get to the variance, I would have to square that number. 4.3. I'll just go 4.5356. I hit the square key, so that's the standard deviation, and this will be the sample variance right here. There it is. All righty. So you might be thinking, yeah, just show me how to do this in Excel. Fair enough. A couple ways you can do it. The same values. We can use this thing called Descriptive Statistics, which is fine. You would have to make sure the data analysis add-in package is on your Excel. Let me bring up Excel. I know how to do it pretty well on a PC. I'm not sure on an Apple, but it's doable. But with the miracle of Google and YouTube, I'm sure you can Google it and figure it out. But that's that's just only if somebody wanted all those other values. But we can just get them specifically without. So if I go over to data, yeah, I have the data. Oh, there it was there. It was over to the right. The data analysis. Oh, why does this keep moving on me? Over there to the right, there it is, data analysis. But if it's not there, it can be added in. Here it's on a PC, it's file. Oh, what is it? Options? Well, I don't see options. Maybe I hit more here. I should remember how to do this. Yeah, more options. Add-ins. But at Apple, you can get there. It's a little different process. I don't know the process, but I've had students ask me before in face-to-face class and sometimes play around with it after class, and they do the same thing. They just look up how to do it, and then then they get it. So yeah, analysis tool pack. That has to be added in there. It's weird. You actually have to hit the go before the OK. See, I don't have to have all those other ones checked. I don't have to, but mine's already, it's checked because it's already there. But then you click OK, and if it wasn't there, then it would show up at that point. So. But I bet you can Google and find just a delightful YouTube video that show you how to do it. But anyway, that was under the data analysis. It's descriptive statistics. I may not type these numbers in, but it's descriptive statistics. Then you got, well, you got to tell it what. First of all, you got to put some numbers in there, and you got to tell it what range, and then output. What I always do in output is I just put the first cell location wherever I want. I don't worry about putting the ending part. What I do is put the first cell and let it spit out whatever it wants, and then this summary statistics has to be checked right there, and then it'll spit out what I had. All right. What I had here. But we don't need all that if we're just going to get standard deviation. I'll show you how to do this. There are those same numbers, and these are sample values. There they are, the 4.355 and then the 20.5714. And a bunch of other stuff that we're not going to worry about in this class, a little more. Kurtosis. That sounds like a medical condition. Hey, doc, my kurtosis is acting up again. I need some more meds. You might be able to use that one as an excuse, if we ever get back to normal again, but, you're sick one day, you don't want to go into pretend like you're sick, and don't say I came up with the idea. Start coughing and say you can't come in because you got kurtosis. All right, let's see. Anyway, here's what we're going to use. Here they are, the Excel commands. So you put your data in there. And like I say, you're going to watch me do this. I'm not going to redo it for these numbers. You're going to see me do it for a homework problem. So there's no point in redoing these numbers. Pick a cell and then just type in whether you want, the S is important for sample because it'll be P for population. So you see how my data is in I11 through I17. So you just pick whatever cell you want your command to be in and then put the cell range. Boom, there you go. That's why you don't really need that thing at the top of the page. And I'd mentioned earlier that standard deviation is usually more popularly used here. So because one thing about standard deviation and variance, especially you kind of, by themselves, they don't really tell you all that much, the number itself. But when you pair it up with the mean to kind of come up with information about data sets, that's when, things start happening. For example, if we have an exam and we say, okay, the mean was 83, the median was 84, and the standard deviation was 9.7. Well, that's hard to tell. Does that mean the scores were really far scattered or not so far scattered? That number by itself doesn't always tell you a lot. I mean, it's an important number in statistics, don't get me wrong, but it's hard to really just get a concept of it by itself. So we're going to actually see how it works coming up, how it pairs with the mean to give us information. Now, all this example is showing you. Now, this is important here because I made sure that the means were the same number, because there's a way to do it if the means aren't the same number. If you have two different data sets where maybe one number, a lot larger set of numbers is larger than the other, and you're trying to figure out which one appears to be more scattered. Yeah, we'll talk about that. That's a pretty easy calculation. But so while the number itself doesn't mean anything, if you look at these two data sets, so there's the one that we originally had, the mean of 9.2. I took 5 numbers and I made sure that they were going to have, the same mean of 9.2. But notice with this new block of numbers, see how close together they are? you know, they're clustered pretty tightly together, and the other ones are more spread out, right? So what I'm saying here is all that guarantees it tells you is that you know that the standard deviation for the second data set is going to be smaller than the one for the first data set, which you can see 0.8366 versus 3.34, whatever. But like I said, so while the number itself may not mean that much, but you know, you can definitely tell that the one on the right was going to have a smaller standard deviation because they're closer together, more scattered. All right, so don't worry about having to do something like this. It was just an illustration here, but we're going to see how to use, yeah, here's what we're going to do. We're going to use a calculation, which isn't too bad because you're going to have technology to be able to get the, I don't know if Excel has a coefficient of variation command, probably not, because it's real, because all you're doing is taking the standard deviation divided by the mean, so you're not, it's not really anything all that fancy. So if you're comparing two different data sets with different means, well, not so much even the different standard deviations, but the different means is the key. Because you can't visually tell which one's more scattered if they're different means. Like the one above, that was the key. We were comparing apples and apples there together, basically. But they're different means, not so much, because you have to consider the standard deviation in relation to the mean. So it's a real straightforward calculation. You just take the standard deviation of your data set, you divide it by the mean of your data set. So for this particular example, those same numbers we were using, you take the standard deviation, which is 4.536, divided by 7.714, and just multiply it by 100 to convert it to percent. So you get 58.8%. Now, one thing I like to mention here, there's no limitations here on this value in the sense that the coefficient of variation can be a number over 100%. It can be well over 100%, because you could have data sets that are pretty far scattered where the standard deviation is significantly greater than the mean. Of course, I guess there is one exception where you couldn't calculate the coefficient of variation, is if the mean was 0, because you couldn't divide by 0. But otherwise, yeah, you could have a larger standard deviation than you do mean if the numbers are really spread out. So yeah, if you did one of these problems and got 212% and you automatically think, oh, I must be doing something wrong here. Not necessarily, not at all, because there's no limitations on what that value can be. I can't remember if that comes up in the homework or not, but it certainly could be on the exam, even if it's not in the homework. Okay, so here's one where I'm taking two data sets. Here's one that has a mean of 50 and a standard deviation of 20. Then we have another one with a mean of 200 and a standard deviation 40. So if you were only comparing standard deviations, your instinct might be, hey, 40 is bigger than 20, so that means that's going to be a more scattered data set. Well, that's the whole point. You can't do it that way unless the means are the same. You know, if one has mean 50 and standard deviation 20, and the other one has mean 50 and standard deviation 40, then there's no doubt the one with 40 is going to be more scattered. But this one, you just quickly do the coefficient of variations, let's say, which isn't that hard, and that's how you compare coefficient of variation. So the first one, you take the standard deviation, which is 20, divided by 50, that's 40%. The next one is 40 divided by 200 times 100, which is 20%. So actually, I would claim that the first data set has more variation because it has a larger coefficient of variation. So like I said, that won't be difficult to calculate, because like I said, with the Excel, you can do the mean and standard deviation commands real quickly, and then just divide the standard deviation divided by the mean, and you got it. So that's not going to be too bad, I don't think. Thumb down here. The standard score, the z-score, which that'll be coming back up again later in the second unit of this course, and third probably. The z-score. Also, let's call it z-score more than I do standard score. It basically represents the number of standard deviations a given value x falls from the mean. And it's also standardized value. Like, for example, let me come over to the scratch page for a second. Now, you're going to be using this calculation. You're not going to be doing it in your head like I'm about to show you here. But just give you, I'm using easy numbers here. Suppose that the mean was, I don't know, 50. And the standard deviation was 10. And you have a value of 60. That would have a z-score of 1. Because if you take 50 and you add one unit of 10, adding 1 times 10, that gives you 60, doesn't it? So it's exactly 1 standard deviation above the mean. So the z is 1. And whenever it's below the mean, it'll be a negative z-score. So let's say it's 30. 30, if you take 50 and you subtract 10 twice, in other words, 50 minus 10 is 40. Minus another 10 would be 30. If you subtracted 10 twice to get to 30, that means it's 2 units of standard deviation, but it's in the negative direction. So the z-score would be minus 2. But like I said, you're not going to be doing these in your head. You know, that's why I picked easy numbers for this illustration. But it's a simple formula to calculate. Yeah, because we're going to have z-scores that are, you know, 1.53 and stuff like that. But so nobody would expect you to figure that out in your head. So here's how you do it. You take whatever data value x that you're trying to find the z-score of, you subtract the mean, and then you divide by the standard deviation. But notice how I wrap parentheses around that. I talked about that, I think, last time regarding something. I remember talking about that you make sure you don't, you know, that you don't divide the calculator. You either hit enter or you put parentheses around it. So let me do it real quick here. So this I'm doing this wrong on purpose. So I'll use the one, actually I'll go the first one, which is 60. 60, the one I did in the scratch page. Minus 50. So this is all about just reminding you of the order of operations. I hate for you to be frustrated, you know, doing a problem and you're spending too much time on it because of this mistake. That would be, you know, that would be bad news, because I hate for you to waste your time, valuable time. If you did that, that's no good. So if you use parentheses, yeah, I see people do that. I'm not getting the right answer. I'm pretty sure I'm doing it right, but it's calculus. This works. Or you have 2 correct ways to do it, but then the one incorrect way. You can go enter first if you want to, then divide by 10. That's acceptable. So you have two ways you can do it, whichever you prefer. There we go. So watch out for that top one. So hopefully I've gone over that a couple times now. So those of you paying attention there, and hopefully that will eliminate anyone making that mistake. So okay, this I'm just going to mention. So if you don't have to know this by definition, but if your z is negative, that means your value is less than the mean. If z equals 0, that means the value is the mean. And if z is greater than 0, value x is greater than the mean. I believe it was last week, could have been the first week, but I know it's come up. I don't remember which week, but the kind of first brought up the term outlier. I think when I was doing that dot plot was when that outlier came up. It's kind of, so here's kind of another way to sort of, I talked about there'd be other ways to define it. Here's one of them. So one way you can do it is if your data values, z-scores, if they're outside the range of -3 to 3, we can categorize them as outliers. So if your z-score was 3.5, you could safely say that you consider that value to be an outlier. And here's just 3 z-score calculations, nothing fancy here. So here's the mean 52, standard deviation 8. We're going to find the z-scores for these given values. So we take 64 minus 52 divided by 8, 1.5. 38 minus 52 divided by 8 then would be negative 1.75. And that one will be 0. 52 minus 52 divided by 8, which is 0. I'm not going to bother to put these in the calculator since I just showed you the example about using the parentheses and whatnot. But I think this was one of the problems where it came up one time a few semesters ago, where somebody was typing that in. I'm not getting the right answer. It was the error I pointed out. Yeah, it might have been where this first came up. But I just showed you that, so I'm confident now you can do that with no trouble. Yeah, but I had not mentioned the parentheses thing in the calculator when the person asked me that. Now, this one, I've been known to put this kind of problem on an exam, so we'll pay attention to this one. So we're going to use z-scores to determine the better relative position of a couple of different test scores. You know, z-scores are kind of, it's a position where that data value kind of ranks, you know. Let's say if someone, you know, you take an exam and whatever, regardless of the mean and standard deviation, you know, if your z-score in that exam was 1.8, you know, and somebody else's was 1.3, that means you had a higher score. And if they were ranking them, you know, you'd be at a higher, the 1.8 would be higher than a 1.3 if we were ranking them from top to bottom. So, yeah, so it's kind of a measure of position also, which we're going to talk more about measures of position coming up. But that's one thing it does. So we're going to take this, so it can be the same student, same person, taking a stats, you know, and an accounting. Okay. Now let's say on the stats exam, you had a mean 80 and a standard deviation 10. Now, we have an accounting exam, which was apparently much more difficult here. Had a standard deviation, a mean of 65 and a standard deviation of 12. And a student scores 90 on the stats exam and an 80 on the accounting exam. Which score has the better relative position to the rest of the class? And all that means in plain, simple English is the higher z-score. Yeah, that's all that means is the greater z-score. Now, you might not care. I'll talk about why you would care, but you might be happier. Obviously, you made a 90 on one and 80 on the other, but maybe, you know, the accounting exam might have some sort of adjustment to it, maybe, or something, since the scores are so low. So it might work out anyway, but let's just do this calculation and not worry about all that. And so the z-score for the stats exam, we made a 90. We subtract the mean of 80. We divide it by 10, which is 1.0. The accounting exam, 80 minus 65 divided by 12, 1.25. So we actually, ranking-wise, did better in respect to the class. We did better on the accounting exam than we did on the stats exam. You know, like I said, that might not make you feel any better or whatever, but who knows? Maybe this particular school has some weird policy where, you know, up to 1.0 on the, maybe they do it, but z-scores up to 1.0 is a B, but if your z-score is greater than 1, that's considered to be an A or something or another. I don't know. I've never heard of that, but I mean, that's sort of like a type of curve somebody could use, but usually it's done a little more sophisticated than that, which we'll talk about later using percentiles and stuff. But anyway, but just hypothetically, that's one way it could be done. Let's say if it was done that way, if you were above 1, that would translate to an A. I can't imagine a 90 not being an A though. So, but anyway, whatever the case may be, you still did better than more people in the accounting class because you got a higher z-score. So that's all you're gonna have to do. That kind of question. And it could be a tie if it calculates to be the same, whatever, exactly the same, not rounded, whatever. So you could have, usually I ask it where, this case I would be stats is better, accounting is better, or they have equal relative position, which is possible. For example, if I change the accounting score to 77, 77 minus 65 would be 12. 12 divided by 12 is 1, 1.0 exactly. So we would have had a tie. Shapes of distributions. We have what's called uniform. Now, perfectly uniform means the heights are all exactly the same, but we sort of roughly define them as uniform if they're kind of close to being the same height, so it's not precisely uniform, and the mean and median should be very, very close to each other. In a precise uniform distribution, they would be exactly equal. But we would visually speaking, we could safely define this as uniform because the frequencies are kind of all about the same for each of these. So now we have one that's called symmetric, but it's not uniform, because actually uniforms are also symmetric. But this one we're defining as the uniforms, the symmetric, so excluding uniform, because the uniform is its own category, in other words. So and once again, there's perfect symmetry versus just approximate symmetric. So we're looking at just approximate here. So, and the way you'd kind of visualize this is if you kind of drew a line right here in the middle and you folded the graph over, it would look the same on both sides. So hopefully you can kind of see that one for this one if you visually folded this over. It looked the same as you flipped it over to the other side. That's essentially what symmetric is. And it could, it'd be more shapes than just that. You could have a different type of symmetry shape. But the idea is if it folds over in the middle, yeah, I know what I'm saying. It doesn't have to be symmetric because it rises up in the middle. Heck, it could lower down. It could start out and make a V shape. It could be a V shape and still be symmetric. Yeah, so it's not because it raises to the middle. That's not what makes it. It's the folding over and being the exact same on the other side. Now we have one, it's called skewed left. This will not be difficult on the test, but if I remember correctly, unless I got rid of it, I don't think I did. I don't know. Maybe I did. One of the homework problems is a little bit tricky on this, but it won't be that tricky on a test. Well, maybe it's not even there anymore, hopefully, but visually you're going to see more data that's to the heavier side, larger numbers. It gets heavier in frequency to the right. So anything that's heavier on the right is actually called skewed left. That seems backwards logically, probably, doesn't it? You think that would be called skewed right if it's heavier to the right, but it's not. It is skewed left. And actually the median is larger than the mean. I think where the tricky thing in the homework, if it comes up, I'll go ahead and mention this in case we don't see it, but it's because I think one of these ones that the median was larger than the mean, it was less than the mean, but it turned out being so close that they still ruled it as symmetric or something or another, which I didn't like that because it in a way, it went against this definition. So it makes that tricky for students in that sense. But it's actually, if they're very, very close to each other, they're probably not skewed in reality. Like, for example, if the median was, I don't know, 3.46 and the mean was 3.42, yeah, one of those numbers is bigger than the other, but not by enough to where it would probably look skewed, really, or whatever. So yeah, that's not going to be tricky on an exam or anything, but let's just keep that, reference there. The median's larger than the mean, which is the same thing. Be careful with this though, because median larger than the mean is exactly same as saying the mean is less than the median, like inequalities. In other words, let me go back to my scratch page. So just kind of be able to, reverse that wording if you needed to. And okay, we're going back to kind of simple algebra here. I do believe those are exactly equivalent, aren't they? They're the same thing. So you can, in other words, saying that 6 is greater than 2 is equivalent to saying 2 is less than 6. So anyway, that's what I was saying when I mentioned that. So now we come over here to skewed right. Okay, makes sense. If skewed left's going to be weird, skewed right needs to be, at least it's exactly weird, just the opposite way. So if you've got more data on the left side, the lower end, higher range of lower end numbers, we call that skewed right, with the median being smaller than the mean, which is the same thing as saying the mean is greater than the median. All righty. Now remember, you can refer back to this, when you're doing a homework, or you won't even need it. Usually on a test question, I just give you a graph and let you pick which one it is or something. So it's usually pretty easy. Now here's one I used a dot plot, just kind of played around, put in a bunch of numbers in there. I typed them. I think I probably clicked and dragged and repeated a bunch of numbers, but I did it this way on purpose. You see it's a bunch of ones. I don't have the original data set there, but we don't need it. But it did a dot plot. It's a bunch of 1s, 2s, so 1 through 7. Next one looked like I did 1 through 10. So you see on the graph on the left, it's heavier on the right side. So that means skewed left, which means calculation-wise, the median back up here should be larger than the mean. Yeah, which is the same thing saying is mean less than the median. But median is larger than the mean. But so let's look at that. So now also I did a calculation here. I used the descriptive statistics. So here you go. The median is greater than the mean. Quite a bit greater. That's like I was telling you earlier, there was a problem, if it's still in the homework, a little tricky because they were so close to each other, even though one was larger than the number, it doesn't really look skewed. But that one's enough of a difference where you see it does look skewed too. So I did the same thing over here. I made sure there were more numbers on the lower end of this graph. So that one is skewed right because it's heavier on the low side. So this one means that the median should be less than the mean. And it is. The median is 3 and the mean is 3.4. So the median is less than the mean. So the numbers pan out to that graph. In other words, they match that rule matches that graph then. So, all right. This tells you how many numbers I used. 90 for that one and 117. But yeah, like I said, I used a click and drag on the corner. There's no way I manually typed in that many numbers. All right, what is this? Okay, this is if you're kind of curious, you don't have to worry about this. But we haven't even got to the population variance yet or whatever, but sometimes it's just the reason why it's divided by n minus n instead of n. Actually, it will be used I probably should have put this at the end of a different section at the one after we do the population, but it's already here. You don't have to worry about this. And there's a lot of reasons. One of it, if you're trying to use the sample variance to estimate the population variance, if you divide by n-1, you're actually overestimating it a little bit. So, because when you divide something by n-1, if it's a smaller denominator, that makes a larger fraction. In other words, 6 divided by 2 is bigger than 6 divided by 3. So anyway, that's not important. So I just tried to find the one explanation that had the, that's why this one was a best answer, that didn't delve too much in the mathematics of it, because that's what you really don't want to see. This is the mathematics behind it. But this whole unbiased estimator stuff, that's a lot of math behind it. I can Google it real quick if you want to see. Unbiased, but we're not going to spend any time with it. We're about to do some homework. Oh, I misspelled estimator, or mistyped it, not estimator. Estimator of variance. All right, go away. Get out of my way there. How do I get rid of this? Well, whatever. I'll just bring up something here. But anyway, whatever. All we need is, I think that's, we definitely don't need that. Get rid of that. Why won't that go away? I don't want that screen there. I want this image right here. Oh, that was that. Anyway, well, I think that's enough to see that we don't really want to go through all that, do we? To show that the sample variance is the best estimator for the population variant. Anyway, so that's when you start. This is where statistics, is studied from a, which I have in the past. It's been a long time, but from a more, mathematical basis than we're learning it, just more from a business or applicable type of process there. So. That's if you really want to get all math nerdy there, Yeah, all this kind of stuff usually has some sort of, math underlying thing behind it that you don't necessarily need to use or know, but or care to know. It's kind of interesting anyway, talking about math and even calculus. That's people no longer take calculus in the business degree plan. I'm sure that disappoints you. I know that so that way people are taking the same hours. I know that they added some other business class to the degree plan whenever they did this. I don't know what it was they added. But just so, kind of make it fair that you're still taking the same number of hours, but they got rid of calculus as one of the prereqs for this class. So that's fine. You probably wouldn't have liked my suggestion there. Whatever they added, I would have added, because years ago, there used to be 2 statistics courses. I would have added a follow-up course to this. Not mathematical, just more learning, You can shoot me later if you want to, but it's actually not that bad. It's kind of a continuation. I'd have done that for what I don't know what they added though. But in other words, I support getting rid of the calculus, but I would have added more statistics because that's more, real world applicable for students. Anyway, I figure I can say things like that on, in this format. So you can't throw anything at me. Yeah, so this is the last week I talked about these sections were combined, but obviously it doesn't take long to do a mean, median, and mode. Oh, we could do that one. Let me look ahead here. Maybe I'll see if we get one. There's a few more numbers, kind of the same idea, but let's Ooh, 7 numbers. Now we're getting there. All right, I'll go back and do that third one. I think that's good enough. It's kind of hitting all the highlights here. All right, so let's just 15 parts remaining. What? I'm just going to look and see what all's going on here. Oh, it's a bunch of z-scores. Okay. All right, that's not that bad. Scared me there for a minute. 15 parts there. Sounded kind of rude, didn't it? Okay, so let's just put this in Excel. We can talk about, if you want to see this in the calculator. I'm not sure unless there's enough interest where maybe, because it's the kind of thing I'd be happy to show the same problem like after class. In other words, if you don't feel like we needed to waste time, it's up to you. If you want to put something in the chat or whatever, if you really think it's important to see the calculator now, or if it's only like one person that wants to see it, I'd prefer to wait till the end. Because that way everybody else doesn't have to suffer through it. Well, I'm not saying it's suffering, but But if somebody wants to see it, afterwards, I'll be happy to do it. Come on, data, get in there. Enable editing. Let's zoom here. Oh, why's my zoom not working? Let me try. No zoom. Oh, well. I'm down there in the bottom right corner and it won't. Oh, now I lost my scroll bar. Now where'd my scroll bar on the right go? I can't get back up to where I was. What happened here? I'm gonna have to open these up again. Where is everything? Anybody looking at this can they see what the problem is? Because I got no idea. I was trying to minimize it, thinking maybe that would bring the edge in or whatever, but it just shrinks the whole thing. I guess I'll have to open this up again because I don't know what happened. Something's not right. I knew something was wrong when it didn't let me zoom. Well, I guess I better quit. Now my scroll bar is there. I'm just waiting for the data to dump in there. All right, I'm not even worried about the zoom. I don't care at this point. So there they are. So anywhere over here, I can do the average right here. A1 to A7. So you just put this in any cell you want. 8. Yeah, the only way you're going to have no solution to these is for the mode. Remember last week we learned it's possible for a data set not to have a mode if nothing repeats. So there will never be no solution for these first two. But that could be the answer for the mode. So it has no mode, you just pick no solution. I think we saw there was a median command last week. Seven. All right, check answer. Mode, oh, I can look at that right here. I see 2 7s, so that means 7's eligible for being a mode. But I got to look and see if it's the most of anything. Remember, it has to repeat. Yeah, nothing else even repeats, does it? So 7 has to be the mode. But if they were all, distinct, unique numbers, then it would be no mode, no solution. But it could be more than one mode. So that's why it's telling you to use a comma to separate answers as needed. So let's say if there was another 14 in there, there were 2 14s. You would have put 7, comma, 14, meaning that we're implying both of those are modes. Yay. Range? I mean, I can go ahead and sort this real quick to make it easier. Like I said, for this small set of numbers, it's probably not too difficult, but why not make it as easy as possible, right? Sort lowest. So that way it'll be, now that they're sorted, it'll be the bottom minus the top one. So 14 minus 2 would be 12. Check answer. Look at us go. We're tearing it up now, aren't we? Variance. So this is a sample. It's telling you a sample. Well, we haven't learned population yet, but we will. But it's got to make it clear whether it's sample or population. Later it does. Now all we have is sample. Okay, so I'm going to go to this command in the notes. Scroll back up real quick, show you. I believe it's var.s. Yeah, here we go. var.s. So you just pick whatever cell you're comfortable with. Anywhere. You can type over the ones you've already used. I'll just put it right here. Equals var.s A1 through A7. Oh, whole number. I was just thinking about what was the rounding going to be there, but that's kind of weird. Usually that can come out to be a whole number because it would have been 2 decimal places. All right. Well, actually, this one I don't need a calculator. I mean, you can use it. You don't have to do this in your head, but the standard deviation will be the square root of 16. Most of the time, we're going to need a calculator, just the way this one worked out, because that means the standard deviation would just be 4. But you can put that and just take the square root, put that in the calculator. Yeah, I would not assume the numbers are always going to be this. Coefficient of variation. Okay, that's defined in the notes. I'll come over here and I'll write it out for you so you can see. So the CV, the coefficient of variation, is the standard deviation over the mean times 100%. So let's get the numbers there. Scroll back up. We just got a standard deviation of 4. The mean is 8. Yeah, the numbers are kind of super easy to work with on this one, so kind of wish they weren't, just so we'd have to actually. So it's 4 divided by 8. Okay, once again, don't have to do this in your head, but that's just 1/2, so it ends up being 50%. So 50. Yeah, these numbers are working out kind of convenient. But it's not difficult otherwise. Just need to use a calculator. All right, we're sailing right along. All right, so it wants to calculate each z-score. Trying to think of if there's a quick way to, probably could be a quick. I bet you, now I wish I hadn't sorted that data, because now, I wonder if I can still, I wonder if I can undo this enough times to get back, because it's probably going to do, yeah, okay, that did it. All right. Because it wants the z-score. So I'm going to write just a simple command here and then copy the command. So it's the z-score, and I'll put parentheses. It's your x value, which is an A1, minus the mean, which is 8, divided by the standard deviation, which is 4. So it's the value minus standard deviation. That way I don't have to redo this every time. I do this, and I just click the corner and drag, and that'll copy the formula down for all of them. Then you can do it real quick. That's kind of convenient, isn't it? So we just got to type in all those z values. And, of course, my memory's not as good. There's no way I can memorize all 7 of those. You maybe probably can, but -7.5, -0.25. -0.75. Yeah, so as expected, it's in the original form in the data. -0.25. I think the next one's positive 0.25, but once again, I don't want to be overconfident here. I was wrong. 7.5. 7.5, -1.5, 0.5. Look at us go. -1.5. I don't know if I have to put the 0 there or not. Probably not for the 0 at the end, but 0.25. Wait, did I copy that wrong? That's 0.5, isn't it? Told you, it's my memory. Yeah, consider I'm using the same formula I drew. Yeah, there's no way it's calculated wrong. Or the other ones would have been wrong. So now I have -0.25 and then 1.5. Are there any outliers? Okay, that was back in the definition. It was like in yellow highlight there that I'm just saying it verbally. I'm not expecting you to know it, obviously, but just telling you it's there. You can go back to it. But it's anything outside of negative. If it's not between -3 and 3, it's an outlier. And all of those numbers are between -3 and 3. So we would say no to the outliers. Nothing outside of those bounds. Now, oh yeah, I didn't talk about this being negative and positive skewed. That's okay. You don't have to worry about it. It's telling you right here. Yeah, left skewed is called negative skewed actually, and right skewed is called positive. I wouldn't worry too much about that. Now we have to go back to down here. median. Median is larger than the mean. We have skewed left. So let's compare. That way the opposite of that will be skewed right. Go back up here. The median is 7. The mean is 8. So the median is not greater than the mean. It's less than the mean. So that should be skewed right as the answer. So it's just following that definition. Okay, that problem actually ended. About time for a break time here, but let me see if there's anything I want to take a quick look at here in the homework. I think we should see that one. Could be interesting. I don't think those other two are that bad. There's kind of more conceptual.
Yeah, the last one it comes down to like 0.5 decimal places.
Oh, okay. Okay.
Yeah. And I had a hard time doing that one just because it was so specific.
I think I even mentioned these last week in class, these two here. Yeah, just the mean and the median. I think I talked about those. So even if you weren't here, you can go back and look at the lecture. But yeah, I'm skipping those. Yeah, let's pop this one in. We'll just take a late break and just have a shorter second half. Makes sense to finish this while we're here. Okay, so let's take a look at this. We got two different categories here. Come on now. Come on, open up. All right, here we go. I think obviously now we got two different columns. I'm not going to go so random scattered to where I put everything. So I want to keep the commands for the command. But this is kind of interesting. What was it asking for? Because we can actually only type in one and we can just copy it over to the side. That'll make it more efficient. Was it variance that was asking for first here? Yeah. Okay. Yeah, so I mean, there's a million ways you can do this. But I want to go equal pop. No, I think it's something else. var.p. No, S. P will be later. var.s of A2 to A6. Because obviously A1 is the header. And since I'm not using the dollar signs to lock in any of the cells, I can just grab the corner of it and drag it over, and then it'll do the same command for the next column. Isn't that exciting? So 5 decimal places. Zeros, all of them, at 00137. Standard deviation. That's going to be, well, I'll do it in the same column, but I'll just kind of skip a line for spacing purposes. STDEV dot S. and then still A2 to A6. There they are. Good grief. How many decimals is this going to want? Hopefully not all of those. 4 this time. Yeah, it's weird. You got to be careful when you're looking at these problems, which I'm sure you are, but you know, you might do a couple 3 in a row that the same number of decimal places, and that one was 5, so you might be expecting this one to be 5. But heck, they just kind of randomly change them, it seems like, oh, that one's 4 now. Okay, whatever. So I guess the point I'm trying to make is just don't assume, just look and see. So I'm going to go 0, 3, 7, 0. Maybe I don't need the last 0, but I'll put it there anyway. Zero, 3, 7, 0. Beautiful. Range. Highest minus lowest. I'll do this one. I'll just tell you what numbers I'm picking, and I'll do it without a calculator. Hopefully I do it correctly. But 5.36 is the largest. 5.26 is the smallest, if I'm looking at that correctly. I think so. So 536 minus 526 is 0.10. So I think just 0.1 should be fine here. Fantastic. Coefficient of variation. Which is surprising they didn't ask us for the mean. We have to get the mean now. So I'm surprised it didn't ask the mean as the first command. No harm, I'll do the mean right here. Average. A2, A6. Drag it over for the other one. So the coefficient of variation is going to be the standard deviation divided by the mean. And doing it this way, I can just do it with cell references. So you see that there's your standard deviations in cell A10. And then your mean right there is in cell 12. So I can just, you don't have to do it this way. Just, if you'd rather just divide the numbers in the calculator or something like that, that's fine. But I'm just showing it this way. So it's A1 divided by A12. I could just change the format to percentage if I want to, or just multiply by 100. I think I'll just multiply by 100. Either way will work. And the nice thing doing that is drag that right over to the right for that one. All right, now I got to see how many decimals it wants. Should look. 4. 0.69731. So that means it'll be 6973. Oh, so wait. Get myself confused here. Yeah. So that's already as a percentage because it's multiplied by 100. So $6973. Excellent. Now we just fly right through these. I've already done them. Variance 00395. Standard deviation. Oh, is it 4 again? I hope it's 4. Got to be 4. 0.62849. So 0.628. Range. High minus low. 5.95 is the highest. 5.80 is the lowest. So you subtract those, it should be 0.15. Yes, I'm not recommending you do these in your head. Coefficient of variation, so I've already got that in there. So it's 1.07250. 1.0725. All right. Choose the correct answer below. Well, A is wrong just because of the, without even looking at the numbers. You wouldn't say something has more variation because it has a lower variance. That just doesn't make sense. Let's check for B. Let's see, let's compare the 5-year. Five years do have more variation. The 00395 is greater than the 00137. Higher coefficient of variation. C is weird. C might be the right answer. Approximately this, I don't know. Got to be careful with that. Approximate to within what amount, you know. Well, I'm going to pick B, and if B is wrong, it's going to be C. Okay. I overanalyzed it there, I guess. So, all right, problem solved. Let me check real quick here and see what came up in the chat there. Might have been about when I said the calculator. Data ranges to the Excel. Well, the problems are going to be, they're not going to be like they are here in the homework. They're not Excel data. They won't be massively large, don't get me wrong. So if you want to use Excel, you'll just have to type the numbers in there, but there won't be 1,000 of them, so it won't be that big of a deal, but they won't be, the test won't be in this format. It'll be like in a test review type format. So I guess I'm not, so I don't want, I say no, that doesn't mean you can't use Excel. It just means it won't be able to dump data right into Excel. You would just have to type it in there. But like I said, they're not going to be massively large. So it's not going to be that big a deal. You can still use it with no trouble. So, but if they were in this format, then I guess the answer would be yes, you could, you know, if they were in this format. So yeah, okay, we definitely need a break here. So is about 10 minutes okay, or is that not enough? Or we'll definitely have a shorter second half, obviously. So I have 8:30. We come back at 8:40. Is that okay? I'll take that as a yes, or nobody scream, no!
We'll take it.
I just have a little 10-minute decompress session here or whatever. So, all right, 10, then I'll go, let me go and just bring the next section up here. I'll be, so, you know, step away here. I'll just start talking whenever I'm ready. So 3.3 should be next here. I'll just leave that up on the screen. All right, then. Let's see what. John Swain, are you out there somewhere?
Yes, sir.
Oh, I just wanted there's no big. I wasn't checking up on you other than Golden Knights outdoor hockey on Saturday, February the 20th. NBC
Where are they playing?
at Lake Tahoe. No fans though.
That's funny. I was wearing my Tahoe T-shirt today.
Oh, I bet, you know, I know they've had outdoor hockey games lots of places before, but hasn't Yankee Stadium done it or something like that, or it's like some baseball stadium did it, or?
Yep, they did it at I think Wrigley. They did it at Yankee Stadium.
Okay.
Can't remember if they did one at Citi Field because they did a couple in New York, but yeah.
Yeah, I just think I bet the Tahoe could be interesting because if you sit up high enough, you could probably enjoy even in winter, you know, and enjoy the scenery a little bit. Hopefully, it's up enough.
Yeah, it's not.
But I guess everything's just going to be a big blanket of white, isn't it?
Pretty much.
That's some nice. I've been up in that area. I've never actually stayed there, but I've been to Reno and just kind of drove around and looked. Yeah, it's real pretty up there. Out in winter, it might not look like much, but outdoor hockey, that should be exciting. So I'll have to make sure I remember to watch that game a week from this Saturday. I believe NBC is having it, so it'll be national.
Yeah, it's the Winter Classic.
Yeah. But no fans, it's kind of sad. That's all right. Understandable, I guess. Let's see what we got going on here. Exploring numerical variables. Sounds exciting. Like the way they name these, exploring. We're taking a big exploration trip here, aren't we? Let's talk about what the concept of a percentile is. A lot of people, you know, I find I'd already have it typed in here, but before I did that, and that's okay. That's why we're learning in this. You know, we're learning, and I expected to know that. But like in a face-to-face class, sometimes I'll hide that, or before I start, I'll ask, you know, do you know what a percentile means? And that's okay if you don't. But a lot of people don't. Probably more don't than do, actually. But you know, like if you were told that, you know, you took some sort of exam and your score was the 73rd percentile, would you know what that meant? But then once I explain it, everybody understands it at that point. But it's not obvious to everybody. But it's a ranking. It means that so for the example I used was 73rd percentile. That means 73% of the people did lower than you did, and 27% roughly did better. So it's a ranking position. So that's what I'm saying. It doesn't mean that you got 73% of the questions Right. Now, just by coincidence, that could have happened, you know, but that's not what the definition of it means or whatever. So like this one, 85th percentile means 85% of the values are less than the value that represents the 85th percentile. So percentiles are used quite a bit. You know, if I think they use percentiles when they talk about like little baby development and child development and things like that, not just babies, but you know, like take a little baby there and whatever, I'll just say 6 months old or whatever. The doctor might tell you, okay, your baby's in the, you know, 48th percentile for weight and, you know, 62nd percentile for length. I guess babies aren't quite vertical then, so I guess you measure them in length and not height. But I mean, so obviously as a child gets over, they would just say height, you know, whatever, like a three-year-old kid or something. But yeah, so that's, you probably, maybe you weren't sure what that was and didn't ask or whatever, but anybody's, yeah, that's sort of what that means. It's just how comparing values to all babies, the data that they have basically. I don't know whether that when I take that data, that could just be, I don't know if that's just for that medical practice or how it's being calculated, because I'm not sure how they would get access to more data than that. I don't know. But anyway, but that's just what, at least that's what it means, regardless of how they're collecting the data. So, which isn't that critical. You know, obviously for the height, you know, unless you're counting on the kid playing basketball, it probably doesn't matter that much. But weight, you just want the child to be in a healthy weight range, obviously, which, you know, that's all that really matters. But that's what percentile essentially means. Now there's some different ways to do this. Here's one way to do this when you talk about, we're going to be using percentiles in more detail later on. But here's one way you can do it from the list of numbers. Excel, I'm not sure how Excel does it, but Excel gives kind of different answers sometimes than what other methods do or whatever, but that's okay. So I'll talk about that when we get to what's called quartiles. So just kind of be careful on some of this using Excel. Anyway, so to find the percentile from like a list of numbers, and the subscript is whatever the percentile is. So P sub K, you know, so P73 would be 73rd percentile. Now you're looking for this value L, which is a location value. I'll talk about that here in a second. You take L is the next integer greater than this expression right here. K divided by, now that would even mean this is, you round up. Even if it's a whole number, if the answer was 8, you would still go up to 9. 8.2, you go up to 9. So even if that's a whole number, you still round up. You take K, which is your percentile, divide that by 100, and you multiply it by N. N is the number of values in your data list. And then you go up to the next integer. So, and now what L is not the answer to the problem. L is the location. That means, let's say in a 20 number list, if L was 13, if you got it to be 13, it doesn't mean the answer is 13. It could be by coincidence. What it means is it would be the 13th number in your list after sorted. It's important that these are sorted. It would be the 13th number. So you would count off till you got the 13th number. Then that number would be the answer. I think this is much easier for me to show you than it is to explain it verbally. I think you'll understand it better after you see this, because it's hard for me. I don't think I explained that perfectly verbally. Anyway. Sorted values, and we want to find P40, the 40th percentile. And there's 20 numbers in the list. So we take 40 divided by 200 and multiply it by 20, which gives us 8. But we actually, even though that's a whole number, we still go up to the next integer. Even if that's a whole number, we still go. So I'm glad they did this example this way. I got this from another book. Goes up 8, goes up 9. L would be 9. So what you do is you count through the list, you go to the 9th number, and these are sorted. They're 2 rows of 10, but it's, you know, still one set of 20 numbers. The 9th number would be that 14 right there. That'd be the 10th number, would be the 18th, so it'd be 14. So we would say the 40th percentile is 14. Here's another one. 73rd. You take 73 minus 100 times 20. And it's 14.6. We go up to the next integer, which is 15. So you would find the 15th number in the list. So then there, 18 is your 10th number. So that's 10, 11, 12, right when I'm moving the box there, 13, 14, 15. There's your 15th number right there, 28. So 28 would be the 73rd percentile. Now, what we're more interested in doing for testing purposes, and I don't know what's in the homework yet, but this stuff, the quartiles, this is definitely, you know, on the exam. But now this is the one thing I don't know that now the Excel answers may match. I'm going to show you a couple of ways to do this. I don't know if I would trust the Excel answers. The calculator is good for this, but actually you can do this manually, because I'm not going to give you like 5,000 numbers, and I don't think the homework has anything that rude either. But I've seen, because I don't know what algorithm the Excel is using for this, but sometimes you get answers that won't match what the homework's expecting you to tell it. And sometimes it will. So I try to avoid Excel on this to make sure that I get it right every time. So this is one where I really want to make sure I show it to you in the calculator. And if you don't have that calculator, I think there are apps for it. I got one on my Android, like a TI-84, sort of looks like a TI-84. It's free, I think. Quartiles split them. They're actually specific percentiles, but they're split in quarters. So the first quartile, called Q1, is the same thing as the 25th percentile. So it splits the lower 25% from the upper 75%. The second quartile, Q2, is where 50% are below, 50% above. So Q2 is also what we know as the median. That's the same thing, second quartile. So it's kind of interesting that median, 50th percentile, and Q2 are all exactly the same thing. Okay, I created some excitement with that, didn't I? Okay, so okay. Yeah, so they're all the same thing. Q2 is the median, 50th percentile, and the median Q2. Yeah, they're all the same thing. So, and then Q3 is the 75th percentile. So you see, it's broken down into 25% sections, and you know. Now, they don't have to be symmetric in shape. In other words, it just means how many values are in that group. In other words, so the value of the numbers themselves is irrelevant. But let's say there were 24 numbers, regardless of the values. You know, you would have 6 of them would be in the first quartile, another 6 between Q1 and Q2, another 6 numbers in here, and then another 6 here. All right, so now the way you do this from doing it manually, but like I said, I'm gonna show you the calculator. I'm a little concerned about Excel doing it. I don't trust it. but the calculator is 100% trustworthy. And this method is 100% trustworthy. Is sort the values. I don't know, maybe on my test they're already sorted. I don't know, hopefully so. Because if you're not, I know you don't have the advantage of using Excel, or at least it's not a very long list if it's not sorted, at least anyway. So they got to be sorted to do it. Now, not in the calculator. Let me remind you. I'll show you in the calculator in a minute. Do not have to sort them for the calculator. You can enter them in just like they are, and the calculator takes care of that. But they have to be sorted to do it by this manual technique. All right. So I sorted them. Now, actually, what you do is you find Q2 first. So you split the entire data set in half. So it's like what you're doing is you're finding Q2, which is the median for the entire data set, and then the other two quartiles would be the halves of those halves. In other words, you take the median of the lower half and the median of the upper half. So you're not going like Q1, Q2, Q3 in that order of solving them. You're actually doing Q2 first, then Q1, then Q3. Okay, so I sort this one and I found 9. Now, one thing that's very important here is I want to make sure that, in case my eyes didn't trick myself here, that I have the same number of values to the left and right of 9. I count 7 numbers to the left of 9. I count 7 numbers to the right of that 9. Okay, so that's what I want. That's it. That's for sure my Q2. That's my median is 9. Now, to find the other quartiles, I circle that. That's why I use these parentheses. Other than we take this 9 that we found for Q2 and we ignore it, toss it out. It's still the answer for Q2. And I put parentheses, meaning that we're only working with the lower 7 and the upper 7 now at this point. So then Q1 will be the median of the lower 7 numbers, which will be that 4 right there. And then Q3 will be the median of the upper 7 numbers, which will be that 12. So that means the quartile values are Q1 is 4, Q2 is 9, Q3 is 12. Now I'm going to do a homework problem, so I'm not going to retype this same one, but still using the one-var stats command. Now, one thing I'm mentioning here, because that list of numbers, you can't see it here, but I'm just telling you that because when you scroll down, you can't see them. But the first 5 numbers in that set, they're in this list. You just can't see them. They're in L1. They're before that first 10. So I entered them in there as is right here. Did not have to sort them for the calculator. So like I said, we'll just do a new example here in a little bit. And so you get them in there and you go, so stat edit list, same command, get the list. Second, quit, go back to calc and you go one-var stats. Now normally we do one-var stats. Let me clear this out. I'll use that same data set that was already there. Stat, calc. Until now, we didn't do this. Yeah, where you see, actually you see the Q1, but you just arrow down to get everything else to appear. That's as far as it goes right there. Now, of course, we just defined that the median is Q2. So there it is, Q1, Q2, Q3. That was for a different data set. That was for a smaller data set. But anyway, I think it was, what data set was that? Let's see. It's kind of pointless to do it for 5 numbers anyway, but it's not worth it. But let's see if that was, oh, that were these numbers. Okay. So there were 7 of them. Yeah. So anyway, you can't see those numbers, but I promise you, I put them in there in this example. And then look over to the right screen. Let me arrow over there. Q1 is 4, the median, which is Q2, which is 9, and Q3 is 12, which is exactly what I got doing it this way. 4, 9, and 12. So you're free to do whatever makes you happy there. If you'd rather say, I don't feel like typing those in a calculator, that's fine. Or if you say, I don't feel like sorting and arranging them, that's fine too. All right, now that's all fine and dandy. You know, we learned how to calculate medians before, you know, where if you have an even number of numbers, that means you average the middle two. Well, let's talk about how that affects the other quartiles. So this one has 12 numbers in it right here. So if we were just back where we were last week talking about median, we would have averaged the 14 and the 15 because they're the middle two numbers. So you average 14 and 15, you're going to get 14.5. So now here's an interesting question. With that last example, when we had one number in there as the median, we tossed it out whenever we were finding Q1 and Q3. So does that mean we toss out both of those numbers to find the quartiles? No. When there's two of them right here that we average, we use both of them. We just take the first number and it goes in the lower half of values, and we take the second number which goes in the upper half. So we use both of them, but when it's one number, we throw it out. When it's two, we use both of them, one for the lower, one for the upper, and you see that you have 6 of them on each side. 3 and 3 is 6. And you have 6 numbers here. And then now so then the median Q1 will be the median of that set, which will be the 9 and the 10, which will be 9.5. And then the median of the upper set, 20 and 22, will be 21. And then there are your values. So here's the same data set, but I'm just mentioning right here that you just can't see the 8 in the screen. But it's there. And you come over to the calculator screen, there it is, 9.5, 14.5, and 21. Like I say, we'll do some live action on here in a minute in the homework. This one's I wrote it in 3 rows, but that's still one set of data. It's you know, okay, this is a little tricky. You could do it this way, or just stick it in a calculator or whatever you want to do. But sometimes people ask me, is that like 3 separate rows of 3 different problems? No, it's one set of data. This might be a little tricky. So what I did down here is I just rewrote them as one long string here, you know, to make it easier to visualize than trying to do it this way. So let's just work with that then. Of course, this is an example where you might say, I'm definitely putting this one in the calculator. Now, I didn't show the data entry, but there are the results. So we're expecting to get 5, 7, and 9 here. Even numbers again. You take the middle 2. And there's, because even numbers, so the middle 2, well, of course, the average of 7 and 7 will be 7. So the first 7 belongs to the lower half. That second 7 belongs to the upper half. We have an odd number 9 values here. So the median will be the middle of that one, which will be 5. We have 9 numbers here. The median of that group, of that 9 numbers will be 9. So there's the 5, 7, and 9. Quartiles. Exciting. Here's a value called Interquartile Range, also known as mid-spread. I don't see that too often. It's easy to calculate, super easy to calculate, as long as you have the quartiles right. The interquartile range is just defined as Q3 minus Q1. And so like for this data set, here they are, 5, 7, and 9. So the IQR for interquartile range would be just 9 minus 5 is 4. Let's see if I mentioned it up in here or not. No, I didn't. I used to have this in the notes before. I mean, I never put it on a test, but you might think, what's the point of this thing? And I'll just tell you this verbally because you don't really have to know it for any reason. And I may write it down and then just in my scribble page here, but this is not anything you have to know. But this value is another way you can look at outliers. In other words, if you take, and you don't have to know any of this, but if you take Q1 minus the number 1.5 times your IQR, anything less than that or greater than Q3 plus 1.5 times the IQR. 1.5 is just some value they can. That's another. So any number less than this expression is considered an outlier, and then any number greater than that expression is considered an outlier. But I'm not going to ask that, so it doesn't really matter. But that's sort of where the IQR comes into play. That's another way to help identify outliers. But anyway, okay. Because other than that, it seems kind of pointless. But the good news is it's an easy calculation. Now we have something called the 5-number summary in statistics. And all that's doing is taking the quartiles that we already have. In fact, the calculator spits out the 5-number summary. It's the smallest, it's the minimum value, Q1, the median, Q3, and then the largest. And that's going to lead to a graph we're going to look at here in a minute. Let me go back up here for a second. So any of these calculator screens, so you can see right here, the calculator screen spits out that 5-number summary. Tells you your minimum value, your Q1, your median, Q3, and then your max. So it's listing that 5-number summary out for you. So you know, if you ever need to get the 5, just the entire 5-number summary, then you can get it that way. Well, obviously, if you do it this way, once you get the quartiles, it's pretty easy to look and see which is the min and the max. But so this one we had even numbers, so it'd be 6 and 7. So the median would be 6.5. And then the 6 belongs to the lower half, the 7 belongs to the upper. So the Q1 will be the average of the 5 and the 5, which will be 5, of course. Q3 will be the average of the 7 and the 8, which will be 7.5. And then we include the min and the max to make the 5-number summary. And here's a graph that represents this 5-number summary. It's called a box and whisker plot. And you won't need technology. I don't think this is even in the homework, but I think it's on the test. But actually, as long as you know how to get the 5-number summary, you'll be able to pick the correct plot. That'll be easy to do. So it's really, you don't need technology to draw that. Although the calculator can do it. But I don't think you need to worry about it, because if you get the 5-number summary right, you can't miss this really. Okay, so the way this develops is it uses the 5-number summary, and the first thing, which if I drew one from scratch, is I got a number line going from my min to my max. So I would draw a straight line anywhere above the graph. There's no Y value associated with this. So, it just looks better if you don't put it against the number line and just lift it up a little bit where it's more visual. But there's not a height really with this. Everything's on the x-axis. So I have a dot at my min and my max, and then I would put dots at each of the quartiles. So that would be, first of all, it'd be a line with 5 dots. Then I draw a box around the quartiles, like so, Q1 to Q3, and then draw a middle line right there where Q2 is. So you have vertical lines connecting boxes, Q1, Q2, Q3. Hence the name of the graph. It's a box, It's got two cute little kitty whiskers sticking out of it there, doesn't it? So the two little parts sticking out from the box are called the whiskers. So obviously if you see a box and whisker plot and you got a really, really, really long whisker, that means you probably got you an outlier there, obviously, if that whisker is really long. Because you're either, stretching out far to the low side or you're stretching out far to the high side. Of course, you still have, like I said, even though the shapes of these don't be full, I mean, you still, as I talked about earlier, 25% of your data is still, in other words, the number of values. It's just, this can be different shape based on what the actual values are. In other words, this big long section right here doesn't mean there's more numbers in that group. It just means it stretches out a little bit farther to that 11 or whatever, but you still have the same percentage of values in each section. So I guess this is the box and whisker representation for that graph. Actually, I don't know how it's doing the height, why it's choosing the height, but box and whiskers is under, I can show it to you if you want to see it. I can use it for that one we've already got here, I guess. Yeah, I can just do it for this. Now I got to check my axes here, my window. Yeah, I don't need negative. I just go 0 to, oh, not that one, 0 for this one. 0 to, how far did those numbers go? 15 or 20? Wasn't that? Let me try 15 and I'll double check. I need to check the data again. Obviously, I can go a little bit farther. I just don't want to go less than whatever my biggest number is. All right, it's 15. So I may stretch that out, make it 17 or 18. 17 is fine. I just make the Y minimum 0. I don't need that much height. I'll make it like 3 or something. And then I'll quit out of this. And if you go to stat plot, second stat plot, you have to turn that on. Enter, now it's on. And if you scroll down here, the fourth, fifth one right there. I don't know what that other one next to it is. Okay, there we go. That's our box plot. And then we can just hit enter from here. Enter, or might have to, oh, I have to hit graph, I think, up in the right corner. I think I have to hit graph. There we go. So that wasn't the one I just showed you. That was for, so it likes to put it right there at the top of the screen, whatever, no matter how you scale the y-axis. So that's fine. So that was the box and whisker for that data set that was already in the calculator. But like I said, if you can just get the 5-number summary right, you'll be able to pick, as a multiple choice question, you'll be able to pick the correct box and whisker because they'll all have different 5-number summaries. So that's how you'll be able to identify it. Box and whiskers, I don't ask this really on a test or anything, but I left that in there from previous semesters. So I thought it was kind of interesting. So you see if your box is heavier to the left there, smaller numbers, like we talked about before, that means that a shape like this first one, you're heavier on the left, so it'd be skewed right. This one's pretty symmetric looking, and that's heavier on the right side with a longer whisker this way, so that's skewed left. So okay, that finishes this section. Now I'm going to jump over to the homework maybe. Yeah, we're not going to do that entire section tonight, but let me let me jump to the homework here for a second. I'll come back and think about this. I wonder if this one, hopefully it didn't combine anything here. Hopefully it, yes, 3.3 is by itself. All right, it's 5 problems in here. Let's see. I'll just look at the completed problems to see what all the steps are. Okay, that's just a basic quartile. I'm not saying we can come back and do that one. I thought I'd pick something that had maybe more. Okay, I'll do one of those. Are they all the same? Oh, there's one with the interquartile range. That was it? Okay. Nothing else in this section but quartiles. Didn't do any percentile stuff. That's okay. Test will be quartile questions anyway. I don't know. Let's pick one of these. See, these data sets are pretty small. Now, frankly, I forgot what the commands are. We can look them up, but in Excel, but I don't think I would trust it really. But it might work though, but I've seen it not be right before. That's what's concerned. When I say right, it's right by their algorithm. I think it uses some sort of percentile algorithm instead of just breaking it up in chunks like we do. It makes the answers a little bit off. But let's see what, so I'll do this in the calculator for sure. All right. What makes me be in, okay, let me X. Did not open in protected view. Why am I in protected? All right. I still can't figure out why this Zoom thing is all grayed out down there. Oh, well. Let's see. You can sort this if you want to. Not a bad idea. It's kind of trickier doing this vertically. But anyway, I'm going to use color highlights here or whatever. There's 7 numbers, so we'll have 1 number. So I'll just fill that in yellow. That's going to be your median. That's your Q2. This one actually won't be too bad. And then, so then the Q1 will be the median of the lower half, the lower 3. Yeah, you might have more numbers than this on an exam question. Most likely you will. Let me give that a different color. Too dark. There we go. Oh. So there's the Q1, the lower half, the last 3 numbers, 14, 16, and 20. So that 16 is the middle of those 3. So that'll be the Q3. So it would be 1, 14, and 16. Oh, I don't want that. I want this. 1, 14. Oh, I want an interquartile range. This one didn't even want Q2. Okay. Well, all right. But you see, we got Q2 to get the other ones anyway. So the interquartile range is just Q3 minus Q1. So it'll just be 14 minus 1, so it'll be 13. Now, what are they telling me here? What in the nonsense is this telling me here? 3 times n plus 1.
The middle one, it's supposed to be the last one, not the one in the middle, the 14.
Okay, hang on a second. Okay, oh, yeah. Thank you. I typed in Q2 instead of Q3. It's 16. Now that's going to be 15. Okay, I just had the wrong 3rd quartile there. Yeah, okay, there we go. All right, see, Anybody can make a mistake, right? So it didn't need cute. It wasn't asking for the cute, but well, we got it because that's how we got the other one. So, but obviously, even though these aren't asking for cute, we've already been studying how to get the median anyway, right? I'm just looking at this. That was that one. Let's see. I'm just curious if any of them. That's fine that we're doing interquartile range. That's okay. I don't feel like you're being totally cheated without the median here, but I will do a calculator thing in a minute. So I guess none of these are asking for the median. This one, I promised you I'd do one, and I promised you I'd do it in the calculator. Well, I'll tell you what, how about this? Those negative numbers there, that's okay. So how about this one? Or I think the one with 5 numbers there, that's no good. A little trickier. Yeah, this one, I don't like it with only 5. It makes it a little trickier because if you sort them, yeah, let me see. I'm curious what the answer of this one is going to be. I was going to look for so what are those? Yeah, I never put 5 on a test. I don't like 5. 4, 6, 8, 12, 15. And it's tricky on whether or not we, do we average those two? Do we just take the 6? Yeah, I should have thrown this. I might end up removing this problem anyway, but let me put this one in the calculator and see what it does. I think it's going to be the 6, but that sort of defeats the idea of the way we were doing this. Now, keep in mind that these are in order, but they don't have to be put in order here. I'm just going to put them in order because that's the way I know the numbers here. Clear. 4, 6, 8. Yeah, I might end up going in and just removing that one. I mean, so if you do it, it won't hurt you because it won't take that long to do it, but I may get rid of it because I don't like only 5. It needs to really be at least 6 to be worthwhile. So I'm going to quit out of this, and I'm going to go stat, calc, 1 var stats, calculate, scroll down. Oh, it did. Okay, it did average those two. Okay, all right. Maybe I'm making too much out of this then. All right. So I guess that was. So there's a 4 and a 6. So it averaged them and got 5. So it averaged the 4 and the 6. All right. I probably made this worse than it was. Yeah. So and then it just averaged the 12 and the 15 here to make 13.5. Never mind. So let's try this then. Even though I don't like 5 numbers, I think it's going to be okay. So that should be 5. This will be 13.5. So that should be 8.5. Beautiful. Now, I'm going to put these in Excel. Of course, it's about to change the number, so I'm going to use those same numbers. 4, 6, 8, 12, 15. Don't remember the command off. Now, it's going to get the median right, no problem, but it's the quartiles that concern me. I'll put them right over here. 4, 6, 8, 12, 15. I don't remember, is there a quartile command in Excel? I'm trying to think. There probably is. That's how I know I had a problem. Quartile, but let's see.
That one. That's the one you want.
Yeah, but will it tell me which quartile I want, though?
Yeah, you have to, when you do it, so hit double click on that, on the blue box.
Comma, something like that? You put like the range and then the comma or something? Or
Yep. You can
Yeah, yeah.
range, then you
There
need
you
to-
go. Thank you.
Yeah. The
Yeah,
array
it's
and then the
range
comma tells you what
and in comma what quartile you want. Thank you. That's that was starting to
Yes, sir.
it was becoming refamiliar to me there, you know. So D6. So I'll put 1 for now for Q2, just do the median command. All
You
right,
can
so
do the same. It'll do the same thing. And then if you break it down the way that you broke it down into 3 groups, or into 2 groups,
yeah.
It'll do the same thing, and you can put it as the second quadrant or quadrile. Never mind. You know what I'm saying.
I got you, boss. I swear I did 1 or 2 one time where it didn't match, so it freaked me out after that. So I didn't trust it after that once it didn't match. But I guess this one was okay then, at least anyway. So maybe it's safe. Well, all right, at least, do the Excel. Then it doesn't hurt to do the Excel, because if you don't get the happy check mark, then you can just try it again, right? So just keep that in mind. If it didn't match, it might not be something you did wrong. Go back and look at it. I must have, there had to be a reason why I didn't like it, because I wouldn't have just said I didn't like it for no reason. It must have done something wrong there, but
It had an older version in like 07 or something.
is that what it maybe was? Okay, now you could be getting somewhere. It could be, okay, it could have been calculated differently in an older version. Okay, that would make total sense.
Sorry, I'm a little bit of an Excel nerd.
Nothing wrong with that. Yeah, and I appreciate that. You're going to be my guiding light here. Yeah, I totally would buy that 100%, because it could have been just doing it by a different method. Then they just revised the algorithm. So now it's probably perfectly safe. So I think that's terrific. So you're actually just doing everybody a favor there. So everybody catch it. You just quartile, your array range, comma, whichever, then you put whatever quartile you want there. So I don't remember the EX or the EXX. So that's maybe different. Maybe not. I don't know. But it could be revised, edited. That's wonderful. Then now we can probably trust it. So that last problem, let's see how that look. I didn't look at it, but it looked like it had some data involved there. So I say let's do it for this one. Now I want to do the Excel. Oh yeah, there we go. I used to hate it, and now I want to do it. Done. Oh, I got to open the file. That would help. All right. So this goes from A2 to A36. So I'm going to go equal, quartile. Oh, why didn't it let me? You see, I don't know what I'm doing here. Well, to some degree I do, but that should be quartile 1. Now it's not asking, is it still not asking for the median, but okay. Well, if it was asking median, I would still do median, but I would assume that if you do this same command with comma 2, that should be the same answer you would get using the median command. That makes sense? Yeah, if you did this with a comma 2, that should get, but if I was just looking for the median, I just would put median because it's easier than typing for all this. So that should be 14. And then, of course, if I copy this, it's going to be, since I didn't protect the cells, it's going to change the cells, so I'll just retype it. I did not protect the cells. A2, A36. Oh, yeah, okay, now it's telling us right there. So quartile 3. 25. I don't know if there's an IQR thing in there, but frankly, there does in Excel, but there doesn't need to be one when you're subtracting two numbers there, right? So getting the quartiles is much more helpful. So I'm gonna say 25. How about 11? Check answer. Beautiful. All right, so okay, there's no point in doing any more fancy learning tonight. Let me think about this a little bit. We don't need an answer right now. I'll make an announcement, but I guess no pressure. But I can start thinking about an exam. Thinking about it. Obviously, no panic here, whatever. But obviously, I need to complete the material and then maybe have the exam, like a week after that or something when I open it up for a few days. Probably not during class. Well, I'll open it across class days or not. I may not. Well, whatever. I guess I could. Because that way, if you'd rather use class, but I hate because I'm going to keep moving on from here. So what do we got left? We got 3, 4. This isn't very good to tell because this is just in sorted order. 3, 4, 3, 5, and there's 2, 5, which you see at 87 kilobytes. 2, 5 takes about 2 minutes. And that's not even directly tested on because 2, 5 just leads us to 12, 1 and 12, 2. Boy, there's I guess I don't want to push it, but I guess we don't necessarily, do we finish all this next week? Maybe not. I'm not gonna worry about rushing to finish it, but we might, but just by accident, we might finish. I'm just looking at the file sizes, 3, 4, 3, 5. It's 4 sections, but not high yeah, I don't know. Let's say we don't. So maybe at least be a couple of weeks, but should we'll just see. Either way, there's no need to panic or anything, but maybe we'll see better how we stand after next week. But it's just something to think about, I guess, or whatever. So probably 2.5 weeks, maybe 2.5 to 3 weeks, looking for an exam. Well, I figured somebody, now that we've gotten this far along, would probably start, realizing it maybe 3 weeks. Hey, we might have an exam coming up here in the near future. So, all right, I think I'm now officially done with lecture. So I'm